First, let's check out the contact class, just to remind us what we have in there. Okay, we got properties to hold a person's first name, last name, and phone number. And we've got a constructor here and set access methods that we can use to put names and phone numbers into these properties. So what do we need to add to this class so that its objects can be put on our ordered list? Well, as we mentioned in the last lecture when we introduced delete, three things that it needs are prev, next, and owner properties. It also needs a destructor and relational operators. Oh my gosh, we are going to be working overtime. But wait, let's think like an object-oriented programmer here. We've already implemented all these things in linked node, so there is a simple way to get all these things into the contact class. Okay, got it? No? Well, all we need to do in order to add all these properties and all these methods in linked node is to declare contact to be a subclass of linked node, like this. And whammo, it's done. If you didn't think of it, it's not that surprising, because up to now, whenever we made a subclass, we started with an empty class, declared it to be a subclass of a superclass so that it starts out life by inheriting all the superclass's cool stuff, and then we added specialized stuff to it. Here we've gone at it sort of backwards. We started out with the specialized stuff and then added the inherited stuff to that. This is another way that object-oriented programming allows us to reuse code. Why are these set access methods underlined in red all of a sudden? Let's get a hint. Set function in handle class does not need to return the modified object. Oh yeah, we learned all about that in our second object-oriented lecture. And we just declared contact to be a subclass of linked node up here, and since linked node is a subclass of the handle class, that means that we've also changed contact from a value class to a handle class. As we learned in that lesson, and as MATLAB just reminded us, there's no need to return the changed object when you set a value of a handle class. It's not an error, but it's not a necessity either, so let's eliminate these superfluous output arguments right now. Other than that one optional detail, there's nothing we need to do to convert a value class into a handle class. But before we do anything else, let's get this thing up to date with some validation. We're going to put some qualifiers up here in the Properties section that'll guarantee that first name, last name, and phone number are scalar strings. And we're going to replace these three messy if-nargen statements that set defaults for the arguments in the constructor with a nice clean arguments block. Oh, and since we're forcing the properties to be strings with property validation, we can get rid of all 6 of these string conversion functions in the constructor and the 3 access methods. And here we go. Here are the property qualifiers up here in brown. Here's the arguments block in place of those ugly if-nargens. And we've eliminated all the string conversions in the constructor and the set access methods, because they're now taken care of by the property validations. This code is so much cleaner now. Kudos to the MathWorks engineers for adding these validation features to the language. The next thing we need to do is implement the abstract methods in linked node. Remember those relational methods and the disp method? The easiest one is disp, so let's start with that. It's way down at the bottom. We use fprintf to display the name and telephone number on separate lines, followed by an empty line. One abstract implementation done and 6 to go. As we learned in the previous lecture, if even one abstract method remains unimplemented in a class, then you can't define any objects for that class. But I'd really like to try out our implementation of disp before we move on. So let's temporarily comment out all the abstract methods in linked node and test disp. Well, I can leave disp in here because we just implemented it. In fact, the only reason to have abstract methods in a class is to force its subclass to include them. Abstract methods indicate that the designer of the class has a template in mind for the minimal subset of methods in all subclasses and has used abstraction to force that minimum to be implemented. Okay, here's our test. First, we put a contact object in the variable named surf. And since we didn't include the semicolon, MATLAB, as we've seen before, prints the variable name and the equals sign, and then calls the disp function on the object that was assigned to surf. Since we've overloaded disp for objects of the class contact, our disp function is used instead of the built-in one, which would just list the properties with their values. So we get the first and last name on one line, the telephone number on the next line, and a blank line after that. Next, we repeat the same idea for the variable Lord, then the same thing happens. Then we call the disp method explicitly on each object and get the printout that way. So everything's working. Before I forget, I'm going to uncomment the abstract methods in link node. Okay, our next job is the set of 6 relational methods that need to be implemented. So let's get it done. With sorted number, relational operations were easy. We simply compared their value properties, which are numbers. But contact has last name and first name, which are strings. Fortunately, the relational operators work fine with strings, and the order used for the relational comparisons is alphabetical, which is the order that we want for our contacts. So the only issue left is how to handle the fact that each contact has 2 strings. Our first thought might be to compare the last names to see which one comes later in the alphabet, and then if they're equal, compare the first names to make the determination. That would certainly work, but we'd need an if statement, and we would have to put a different version of that if statement in the 6 different relational methods. Also, we have the subclass business contact, in which we need to include 6 relational implementations as well. And you may remember that that subclass includes a company name too. We'll want to include that in the alphabetizing too, and that would require messy nested if statements. And later we might add additional subclasses, which may include, say, middle names, and would result in more deeply nested if statements. But there's a far simpler approach that eliminates all that if statement business and will still solve all your relational problems. Well, maybe not all. You can find plenty of other courses that'll claim to help you with personal relations, but for string relations, you've come to the right place. That far simpler approach is to add a new method to the contact class that concatenates the names into just one name to be used for comparisons. Then the relational operations can be used directly on the concatenated string, no ifs, ands, or buts. Here's that method for contact. This method is just for internal use, so we've made it protected. Private won't work because subclasses such as business contact will need to inherit this method from contact. Note that in addition to concatenating the last and first name into the same string, we're converting the entire string into uppercase to avoid dealing with issues like whether an uppercase A comes before a lowercase a. Now we're ready to implement the methods to overload the relational operators. Actually, we've already sneaked them in at the bottom, just above disp. Pretty easy stuff. What's even better is that all we need to do to solve this same problem in the business contact class is to override name to compare. The other methods will be inherited from contact and will work right out of the box. We'll do that in a minute, but first let's look at that business contact, which we haven't touched since our first object-oriented lecture. Well, that's just sad. Look at this poor thing with all this messy default setting stuff, using NR again 100 times, for goodness sakes. With all these conversions with the string function. This is all so 2016. Let's get this thing up to snuff with some property validation and some default argument setting. And since it's now a handle object, we need to get rid of the output arguments for these setAccess methods. Here we go. Night and day. And now let's override the disp and name to compare methods to include the company name. Here and here. Then let's try it out. First, we create a new ordered list object named Rolodex. Rolodex? It's a card holder. It's been around since 1956, and you know what? Just Google it. And we have a Rolodex containing, well, nothing. You know, we should probably have ordered lists display a better message when the list is empty. You could try that sometime, but for now let's go ahead and put some cards in our Rolodex so it'll contain something. We'll make 5 cards. And we'll put them in cells. 2 are ordinary contacts, and 3 are business contacts. These are, of course, different classes, so I couldn't put them all in the same vector, what with MATLAB arrays being homogeneous and all, so I used a cell vector. Well, let's stick them in the Rolodex. Then let's see what's in there. There they are. All our cards in our Rolodex in nice alphabetical order. Everything is rosy. But there's a thorn hiding in there. Let's see what happens when plumbing doesn't suit old Joe anymore and he decides to try carpentry. Joe doesn't apparently have a lot of imagination when it comes to names of businesses. But let's look at our Rolodex again. And there's your thorn. The things are not in alphabetical order. Remember we had the same issue with sorted number? To keep the list from getting out of order, we had to add code to the setAccess method for its value property that repositions a node when the value is changed. Well, we need to do that same thing for contact and business contact. But this time there are 3 setAccess methods that require repositioning: first name, last name, and company. To avoid having to put the same repositioning code in 3 methods, we'll write one repositioning method that all 3 setAccess methods can call. Now it's time to think like an object-oriented programmer. How can methods in these 2 different classes call the same method? Time's up. Simple. Put the method in their superclass so they can inherit it. So, looks like a linked node is getting a new method. And here it is. We made this another protected method because, again, we don't want this method to be callable from the outside, but again, we do want its subclasses to have access. And by Jiminy, with protected access, they will. We also need to update the affected setAccess methods in contact. Here in setLastName and here in setFirstName. We don't need to add it to setPhoneNumber because the phone number doesn't affect the object's position on the ordered list. But we do need to add it to setCompany in business contact. And there it is. So simple. Contact and business contact, just say the word and it happens. Isn't inheritance the best? One class does all the work and its offspring reap all the benefits. Oh, but one of linked node's children is being left out here. Sorted numbers should use this same method. But hey, that's the perfect thing for you to do on your own. And I'm in too big of a hurry, not to mention too important, to do it myself. All right, time to try out repositioning. Let's try repeating what we did before and see whether repositioning works. Okay, that's the original list. Now Joe switches to carpentry again, and let's look at the list now. And there's good old Joe between A1 Exterminators and Mike Fitzpatrick, right where he belongs. Our Rolodex seems to be working pretty darn well. Of course, we'd need to do a bit more testing before we trusted our implementation enough to declare victory, but I'll do that offline. It'd be a pretty boring video if I recorded all that and made you watch it. Though maybe I should say it would be an even more boring video. But your reward for sitting through all this boring stuff is that you've seen an illustration of the power of object-oriented programming. When we started this lecture, we had two unrelated sets of classes. The first set was a pair of classes named Contact and Business Contact that stored personal and business information. The second was an implementation of sorted lists, comprising three classes: DList, its subclass Ordered List, and the abstract class Linked Node. When we created the first set, we didn't assume anything about lists that might hold their objects. And when we created the second set, we assumed as little as possible about the objects that could go on their lists. Combining the two naturally involves some work. There's no free lunch after all. But if you look at the methods that we needed to add to the Contact and Business Contact classes to make it all work, you have to admit that it is a pretty cheap lunch. Now, speaking of lunch, I'll be right back. Well, that was great. A tomato and mayonnaise sandwich on white bread, bagel chips with hummus, and sweet iced tea. I ate pretty doggone well, let me tell you. And that's good, because now we're going to sum up what we've learned in some high-level concepts of object-oriented programming. And I mean that. I'm going to get quite high level with this summary. And you never want to get too high on an empty stomach. So, these high-level concepts are ideas that you have probably absorbed just by watching me construct objects and use them. But we need to add some names to what you've learned and define some principles of object-oriented programming. We've waited until the end of our lesson to define these principles because, frankly, principles don't mean a thing until you've seen them applied. Now, though, with the completion of the object-oriented implementation of our little Rolodex, you've seen enough to understand. The first principle is called encapsulation. Encapsulation means that all the data and all the methods that work on that data to implement the functionality of an object are combined inside the object. For example, when we made the ordered list object named MyList, its head, tail, and length properties, and all its methods, which together implemented the functionality of MyList, were in effect all stored right there inside MyList. Furthermore, the implementation of an object's functionality, which includes all its properties and all its methods, is distinguished from its interface, which comprises only a subset of those properties and a subset of those methods that are visible outside the object's class. For example, the interface of MyList included only its methods and none of its properties. So when you used MyList's insert method to add the first item to a list, it changed the handle in MyList's head property, but you couldn't look at that handle because head was not part of the interface. Another way to say it is that how an object works is distinguished from how an object is used. The next principle is called information hiding, and it serves to define that interface. Information hiding means that some portions of the implementation of an object are accessible only to methods in a subset of other objects. If a method can't access some property or method in another object, then that property or method is hidden information. Information hiding predates object-oriented programming by many years, but object-oriented programming adopted it in order to distinguish the implementation of an object from its interface. In fact, the interface between an object and a set of other objects is the set of properties and methods that are not hidden from those objects. For example, the interface that contact objects present to objects of the class ordered list includes all of contact's properties and all of its methods except reposition and name to compare. There are three main benefits to encapsulation. The major benefit of encapsulation is that it allows the developer to maintain detailed control over how an object can be used. In particular, you can hide the implementation details from the users of the object so that they can utilize only a limited set of properties and methods. This hiding of implementation details keeps the user from creating their own classes with code that can reach into the existing objects and make changes that might cause inconsistencies or throw errors. Another benefit is that the developer can freely modify the implementation of the object as long as the interface, which is the set of properties and methods that are visible to the users of the object, does not change. For example, if you look at the ordered list class, the user of that class doesn't need to know that it's implemented as a subclass of the doubly linked list class, dlist. We could change it to be a singly linked list, or even a cell vector if we wanted to, and the user's code would still work correctly. The properties and methods that objects of other classes can access to create a list, add and remove items from a list, or display the contents of a list, for example, could be re-implemented if we decided to use a different data structure inside our class. But as long as we don't change the interface, which comprises the names of the accessible properties and the signatures of the accessible methods, the program that uses our objects doesn't have to change at all. And one more benefit of encapsulation is that the user of the class doesn't have to know anything about how the class is implemented. As long as the public methods are well designed and provide error handling, users don't have to worry about making some mistake that will compromise the data inside an encapsulated object. For example, the user can't simply set the head handle of the ordered list class to an arbitrary value. That head handle can only be changed when a new item is inserted and an existing one is removed, or some relevant property of an item in the list changes. For example, when the value of sorted number item is changed to a number that makes it first on the list. Many times the designer and the user of the object are one and the same person. But it's still a very good idea to use these object-oriented programming features when writing large programs. It'll make your program less prone to error, easier to debug, and easier to maintain. An important concept that was introduced with object-oriented programming, and which you've seen in this lesson many times, is inheritance. And as you have learned already, it means that a class can be defined as a subclass and get functionality from its superclass without any coding required. And of course, the subclass can add its own specialized functionality. One main benefit of having one class inherit functionality from another class is code reuse. For example, when we wanted a class to represent business contacts, we didn't have to start from scratch and re-implement or copy existing code from the contact class. We simply took what we could use without change directly from the contact class, like last name and first name, and implemented or re-implemented only what we needed to modify in business class, like name to compare. With that single modification, all 6 relational operators work perfectly for both classes without any change to them at all. Another benefit of inheritance is that it makes specialization easier. A superclass, which is also known as a base class, implements some kind of functionality. And to implement a specialized version of that functionality, a subclass can reuse that functionality and add only what is necessary for a more specific version of that functionality. A subclass of that, in turn, can make an even more specialized version and so on. For example, linked node objects serve one simple purpose: to provide the functionality required for insertion into a doubly linked list. The contact class then inherits that functionality and adds specialized functionality by including personal contact information, names and phone numbers, and implementing relational operators. Business contact, in turn, inherits the specialized functionality of contact and adds further specialized functionality to that, company names and fax numbers, and also modifies the determination of order. Inheritance relationships, along with subclass relationships, can be nicely visualized with a tree structure, as you can see here. Our tree is upside down in comparison to wooden trees. Its root is at the top and its leaves at the bottom. The root of this tree, which is handle class, is conveniently built into MATLAB. And we created two subclasses of that class, named dlist and linked node. We then created ordered list to add specialized functionality to dlist. And we created three subclasses of linked node to add specialized functionality, named letter node, sorted number, and contact. Then we further specialized contact with the business contact subclass. This tree specifies a so-called is-a relationship. You can say, for example, that sorted number is a linked node, and that linked node is a handle. And the is-a relationship is transitive, which means that sorted number not only is a linked node, but is a handle also. This is-a relationship highlights a crucial advantage of object-oriented programming. Consider our ordered list class. It deals only with linked node. It doesn't know anything about contact or business contact or sorted number, and it doesn't need to. It uses only the features that linked node provides. But that's okay for contact, business contact, and sorted number too, because each of these three classes is a linked node. If we wanted to create an ordered contacts list in addition to the generic ordered list, and impose the obvious requirement that only an object that's a contact could be put on the list, we could make ordered contacts a subclass of ordered list so that it would inherit the functionality of ordered list and add class checking to it. Inheritance makes it easy to specialize existing code, and that makes it an extremely powerful feature of object-oriented programming. And inheritance is powerful in the other direction too. We've just presented inheritance from a top-down point of view as a technique that supports specialization, but it also supports generalization. Let's look at it from the bottom up. Suppose we've written classes for some seemingly unrelated objects, like, say, rakes, refrigerators, and petunias. Then we find that we need to include all of them on a list of items for sale in a big box store or an online outlet. Well, the driving theme here again is storing and sorting multiple items in a dynamic data structure. So we'd think about commonality among these sale items, like the universal product code, sale price, and number in inventory, and whatever links and methods would be required to hook them into the data structure. We'd then create a generic handle class that implements only this common functionality for sale items. So instead of specializing, we're generalizing from a set of concrete items to a single abstract sale item, an item that doesn't even exist. This process of generalizing from concrete to abstract is known as abstraction. And it's no coincidence that object-oriented programming provides the concept of abstract class to support this abstraction. We would in fact use the abstract access attribute to make the class abstract the way we did for linked node, so as to prevent the instantiation of objects for items that don't exist. And finally, we'd add a declaration in the classes of the rakes, refrigerators, and petunias that they are subclasses of our abstract class, implementing any abstract methods in the abstract class so that we could make actual objects with them, just as we did with contact and business class when we made them subclasses of linked node. At that point, the generalization is complete. An important concept implemented by object-oriented programming is polymorphism. But you don't have to define an object to get it. We looked at polymorphism in the first class. And by class, I don't mean something you create with a class definition. I mean our introductory set of MATLAB lectures. We looked at polymorphism in the fourth lesson of that class. The word has many meanings, but the most common meaning in programming, and the one that we use in our MATLAB courses, is variation in the behavior of a function of a given name when the number or types of actual arguments varies. A function whose behavior changes with types or numbers of arguments is called polymorphic, and most of MATLAB's built-in functions are polymorphic. As a simple example, if the square root function is given a scalar as an input, it returns a scalar as an output. But give it a vector, and its behavior changes because it returns a vector. And take a look at the help page for the plot function sometime. Its polymorphism is really quite intricate. And we can write our own polymorphic functions that use the built-in functions nrgen and nrgout to determine the number of arguments, and the isa function to determine the types of arguments to affect the function's behavior. I'm talking about normal functions here, and these options have always been available in MATLAB, but object-oriented programming brings a new way of supporting polymorphism. Subclasses inherit the public and protected methods of their superclasses, but they can override those methods. If an inherited method works well for a subclass, we don't need to touch it. We can use it as is. But if the subclass needs to change it, we can simply use the same name and re-implement the function. And it'll be overridden when it's called by an object of the subclass. For example, the contact class implemented a disp function to display the contents of its objects, and its subclass, business contact, overrode that method by redefining disp to display the contents of its objects. When disp is called by a contact object, it will behave in one way, and when it's called by a business contact, it will behave in another way. That's object-oriented polymorphism. And don't forget operator overloading. Operators are nothing but functions whose names are symbols. So operator overloading is another example of object-oriented polymorphism. And that's it for the high-level concepts. But since you've hung in here with me this far, you've earned the right to be let in on a lovely little secret that we've been hiding from you since the very first lesson of our very first course. We've been using MATLAB object-oriented programming all along, and so have you. That's right. Instead of this object-oriented stuff we've been learning here being different from the rest of MATLAB, all of MATLAB is object-oriented, and every variable is an object. It's like, it's like if in the last Harry Potter book you found out that all the muggles were really wizards too. Well, you wouldn't believe it was possible at first. You'd rush back to the earlier books to prove it, and much to your shock, you'd see that their wizardness had been hidden right there in plain sight the whole time, and you just didn't know how to see it. Oh my gosh, I'm getting goosebumps right now just thinking about showing this to you. We are about to pull back the curtain, so sit down and get ready. First, let me just create a few normal muggle-like variables here. And let's create an object, which in our analogy is like a wizard. We'll use a class that we created in this lecture. And let's use whos to see what's in our workspace. In our intro course, we first saw the whos command right after we'd introduced the class function, which returns the type of its argument. And we asked why that class function was called class instead of type. And the answer we gave was, well, a little evasive. Let's listen to that again. By the way, why is the function called class instead of type, since we're checking the types? Well, MATLAB reserves the name type for a command that prints out the contents of a file, as in type the file. Let's get a little tricky here. MATLAB reserves the name type for a command that prints out the contents of a file. That's true, of course. But knowing what you know now, that answer seems a little weak, doesn't it? I mean, why couldn't MATLAB have named the function that prints out the contents of a file print and named the function that shows the type type? And why does whos use the word class in that fourth column? Why indeed? So, as you can clearly see from the class function and the whos function, every variable in MATLAB is an object that belongs to a class. What? Just because MATLAB calls something a class doesn't prove it's a class. Okay, fine. So what would prove that it's a class, Ms. Expert? Okay, good answer. If it has methods defined for it, that would prove it's a class. So, if I could convince you that, say, double has methods defined for it, then you would admit right here and now in front of the 1,000 other people that are listening to this video that I'm right when I say that the type double is actually the class double, right? Okay, I just want to get that straight. So let's, well, how can we find out whether double has methods defined for it? Well, I've got an idea. Why don't we try using MATLAB's built-in function called methods, which lists all the methods of a given class. And if it lists even one method for double, then you will admit that it's a class. Getting a little nervous, are you? Well, here goes. Yeah, I'd say double has some methods. 210 of them, more or less depending on which libraries are installed. For example, if you're running MATLAB Online version 2020A, you'll get 260. But the point is that it has at least one, so like I said, double is a class. And don't feel too bad, I bet not one of the other 10,000 people listening to this video knew it either. Heck, there was a time when I didn't know it. But while we're rolling here, let's check on the string class. Okay, not as many as double, but hey, double's our go-to type in MATLAB. I mean go-to class. So 38 is at least respectable. And there's GT right there in the middle, which we use to put contacts and business contacts in order. Like this. Which proves something that the 100,000 people listening to this video probably suspected, and that is that Mike is greater than Akash. So MATLAB's object-oriented wizards have been hiding right there in plain sight all these years. You just need to know how to look. Look at this, for example. Okay, nothing earth-shaking there. Name's just an ordinary variable whose type is a string and whose value is Mike. And when we pass it to the built-in function upper, it returns the string in all caps. But if everything in MATLAB is an object and every object belongs to a class, then maybe this will work. So when I hit enter, what do you think? Red stuff or not? Here goes. No red stuff. No red stuff. So we are up to our neck in object orientism. Just made that word up. I need to point out something though, and that is that these are value classes. So while name.upper returns the uppercase version of Mike, it doesn't actually change name. That actual argument is still the same as it was. Now let's try the same thing with one of double's methods. Of course, abs returns the absolute value. And here's the dot operator version. Whoops, yeah, that's a bit of a sticky wicket. Yes, X is an object of type double, and yes, double has a method named abs, but no, you can't use the dot syntax to call any of its methods or any of the methods of any of MATLAB's built-in types except for string type. That's why I picked the string type to show you the dot syntax. So for all built-in classes, it's best to stick with the good old-fashioned normal function calling syntax, separating the argument from the function name with parentheses instead of a dot. In fact, as we said before, that's the preferred way to call any method of any value class. So we've seen that the function name methods will list an object's methods. Now suppose you wanted to see a list of a class's properties. You guessed it. Now let's use this handy function to list the properties of the string class and the double class. Not all that exciting. Actually, kind of disappointing. What's going on? Well, the properties function will list only the public properties of a class. Since these are all built-in classes, they have to be bulletproof, so MATLAB is using information hiding. You do not have direct access to any of the properties, only indirect access through well-defined methods that have been thoroughly tested by the software engineers at MathWorks. Of course, we did the same thing with our link node class. Let me conclude with a final example that may be the coolest one of all. It shows a good reason for MATLAB to treat its built-in classes, types, classes, as object-oriented classes. And the reason is that it lets users create subclasses of the built-in types. So, for example, and you definitely need to be sitting down for this one, you can define subclasses of the double class. Oh my gosh, talk about wizardry. To show the example, we're using MATLAB's built-in web function here, which we introduced in the 7th lesson of our introductory course. It opens a website in MATLAB's built-in browser like this. You can just scroll to this section named Subclass Double and check out how to create a subclass of doubles that can hold only positive values. No negatives and no zeros allowed. So if your application needs doubles but they must be restricted to positive values, you can create a subclass of double with just a few lines of code as shown here, and you are on your way. I'm not going to explain the example. The explanation in this document is all you need. Remember, we took off the training wheels 2 lectures ago. You can handle this all by yourself and make me proud. In fact, you can make me even prouder if you were to replace this old-fashioned if-else statement with a brand new, super modern, up-to-date arguments block. So at last it's time to wrap up our introduction to object-oriented programming in MATLAB. We've already given you a very detailed summary of the concepts we've learned in this lesson, and that summary can itself be summarized as encapsulation, inheritance, and polymorphism. Hope you've gotten a good feeling for the incredible power of object-oriented programming. I hope you've also realized how designing an object-oriented program requires a slightly different kind of thinking from the approach of creating a traditional procedural program. You have to think about the data your program needs to handle first and foremost, then come up with a fitting class structure, and finally plug in the methods that provide the behavior. It takes a bit longer, but your code will be more robust and more reusable. For small one-off programs, it may not be worth the time investment to create an object-oriented programming solution, but as the program size grows and has to manage more kinds of data, then a good object-oriented programming solution will make your time investment worthwhile in saving you time and a headache down the line. As I cautioned you at the beginning, despite the length of this lesson, it's still only an introduction to the subject of object-oriented programming. We didn't have the time to cover many of the details, and we omitted some important topics, such as multiple inheritance, class methods, and other things. If If object-oriented programming is something that you want to use in your programming, go ahead. Plan how your data should be handled, define some classes and properties, and get to work on those methods. You've seen enough in this lesson to do most of what you need to do. You'll hit a snag here and there, on your first foray, of course. But you can find answers in MATLAB's documentation and at MATLAB Central. And you've got Google too, don't forget. What would we do without Google? Oh, and you're going to get more exposure to object-oriented programming in the next and final lesson of this course when we take up MATLAB's App Designer, because that thing is 100% object-oriented. We'll use it to build an object-oriented graphical user interface, and that'll drive home many of the things that you've learned in this lesson. And it's actually a lot of fun. I'll meet you in part 1. You're going to love it.